The Jupiter system is a violently hostile environment. Its intense radiation belts can destroy unshielded electronics in a matter of hours. Yet orbiting within this field is Europa. Roughly the size of Earth's moon, its surface is a frozen, heavily fractured shell of water ice sitting in total silence. This diagram compares the total liquid water found on both worlds. While Earth is famous for its surface oceans, the reservoir trapped beneath Europa's ice is estimated to be twice as large as all of them combined. A massive saltwater ocean, shielded from deep space by kilometers of solid ice, makes this moon the most promising location in the solar system to search for extraterrestrial biology. This orbital trajectory map shows a specialized approach. A probe will execute dozens of close flybys, scanning the ice before retreating to safety. These passes map the ocean's parameters, confirming a stable body of water existing for over 4 billion years. Spectrometers scanning the surface have identified organic compounds, the chemical building blocks deposited by asteroid impacts during the moon's formation. The surface also holds a chemical energy source. Jupiter's radiation bombards the ice, breaking molecular bonds, creating reactive compounds for life. While orbital sensors confirm these ingredients exist, verifying active biology requires crossing the ice. We have to leave orbit and go down. Landing on Europa presents a unique mechanical challenge. The atmospheric pressure is near zero, meaning traditional parachutes provide no drag to slow a descent. This sequence diagram outlines the maneuver. To break orbit, the descent vehicle relies on a solid rocket motor. Once jettisoned, a powered descent vehicle takes over. Thrusters fire as autonomous systems navigate the probe to a safe landing among the ice ridges. The battery-powered lander makes direct contact. Its 4 mechanical legs independently detect the striated surface and lock securely into the ice. This hardware temperature table dictates the design constraints. Delicate cameras and actuators must continue to function even as ambient surface temperatures plunge to -100 degrees Celsius. Cold is only one threat. Despite mechanical shielding, the lander's electronics continually absorb Jupiter's trapped radiation. The hardware will likely fail within 20 days. That expiration date forces a rapid operating cadence. The mission must move to the next phase immediately before the lander's electronics die. The lander deploys a nuclear-powered cryobot, which separates from the surface station to begin descending. Using the decay heat from its reactor, the cylinder begins a slow, grueling melt through 15 to 25 kilometers of ancient, solid ice. The cryobot is now isolated, tethered to the surface only by a single, unspooling fiber optic thread. To protect the moon, the interior of the craft was heavily sterilized. This prevents Earth-based microbes from contaminating an untouched alien ecosystem. The probe sinks into a silent darkness, leaving the radiation of the surface behind, and traveling back through millions of years of geologic history. The ice shelf finally gives way. The cryobot breaches the bottom of the crust and makes first contact with the saltwater ocean. An autonomous underwater drone swims out of the cryobot housing and into the vast water column. Cyan lights reveal a dense environment filled with suspended mineral particles and churning currents. This diagram shows the source of that mineral activity. Cold water seeps into the rocky seafloor, heats up through geothermal energy, and erupts back out through active hydrothermal vents. These active vents provide the final requirement, a continuous, stable supply of energy capable of sustaining biological life without sunlight. The drone's cameras illuminate the vents, revealing colonies of bioluminescent, translucent organisms. These are primitive, microbial life forms, thriving in the dark and feeding on the chemical energy expelled from the seafloor. Years later, a human scientific station remains in the Jovian system, observing Europa from a permanent orbital distance. This discovery shifts our understanding of biology. Finding a second, independent origin of life in our own solar system suggests that the requirements for life are common throughout the galaxy. The abyss of Europa did not offer a dead silence. It confirmed that biology can thrive in the most isolated corners of the cosmos, proving that humanity is not alone.